Good morning. I hope you're all well. Last few weeks to go. And at least this unit is coming to a close very fast. How are you all today? Still well? Fantastic. So, we'll cover the last bits today. And as I said, if you don't have the maths background, this won't make much sense. So if you do, fantastic. You'll get the whole lot, I hope. If you've done, well, first year maths 10, 11, 10, 12, this will be just easy stuff for you in that case. If you haven't, you're going to struggle with this, and I suspect in that case you won't look at this very carefully. But the mathematical statistics part of this actually deals with all these ideas, because without the maths background, you don't know what you're actually doing with the statistics. So you understand how you find estimates and what the properties are, and then how you can build from there to confidence intervals, hypothesis testing, all those ideas in the higher stats is very important. So you have this here. For those who will do the high level stats next year, third year, whatever else, will find this really useful. So I would advise you to look at this carefully. Anybody who does any mathematical statistics next year, 3062, I think, will cover most of these kinds of ideas. But other stats units, the applied ones, also will cover similar ideas, especially to do with likelihood and likelihood ratio testing, those kinds of things that you will see afterwards. So very briefly, last week we actually did do the mathematics behind trying to optimize and maximize the likelihood. But the basic ideas behind maximizing a function using calculus is essentially to write down the likelihood function itself. So you want to find the likelihood function, write it down. That's usually not that difficult, because essentially you're writing down the probability of the data, and then you take the log likelihood, because the log function here in this case is far easier to work with than the original likelihood. It has a nice simpler form. Then you must find the first derivative, and then take a look at solving the equation for the derivative equal to 0. But basically the idea here is there. And this isn't simple. If it's just a function of a single variable, even that's not simple. So if you got some weird function with exponentials and logs, you can't solve that exactly. You must solve it numerically. But if it's a likelihood that involves more than one parameter, almost surely you can't solve a thing analytically. You must use some numerical methods. So R has built-in numerical packages to solve these kinds of things. And you can, well, when R actually does fit a model, this is exactly what it does in the background by using this maximized likelihood and using iterations to come to a solution. Now, this isn't simple, and it doesn't always work. It only works, this idea of actually trying to maximize by differentiating only works if the global maximum actually lies at a likelihood point. As simple examples, excuse me, or where this kind of thing fails is, I'm sure you've all seen this idea of the uniform distribution. So I've got a random variable here, say x, that's uniformly distributed, uniform between, say, some numbers a and b, which means it just has a flat PDF. So the probability density function for this one will simply be flat. It will be some value between, well, between a and b will be non-zero. So if this is the total area here is required to be 1, then the height of this must be 1 over b minus a. So it's fixed. If I take observations on this random variable here, so if I've got observations x1, x2, x3, x4, up till xn, say, and I'm trying to find here an estimate for the value of b. Let's make this simple. Let's make this n 0 here. So then it becomes simpler to look at. So that n disappears. That's a 0. And I can change this as well. So I'm going to have here 0 to b, it's flat, and this is just actually b. If I have data here x1 up to xn, now try and write a likelihood for that, for b, because I'm trying to estimate b here, that's my parameter. It's difficult. In fact, if I do have some data like that, what's the best estimate for b going to be? Is the average good enough here? Suggestions? Mean? Median? The maximum? Because I've got data, b is the upper bound, right? All the observations must be less than b, agreed? The maximum is the best I can get. But even the maximum is going to be less than b. Yeah? That's my best estimate, but it's less than b. So you see, there's no way I can get something that's meaningful here. And then if I say find me properties of the estimator, my estimate is a single value. What's its variance? Big deal. Yeah, you've got no idea what to do with this. This is difficult situations over here, and this is not something that's unusual or uncommon. Just often we have these kind of problems in statistics that just are intractable in many ways. Now the best I can do is to repeat this several times, and so this is where simulations come in, which are really magic for this kind of stuff. If I simulate n observations from a uniform random variable of this kind, 0, b here, where b is unknown, and I look at the maximum in each case, I've got some idea in that case of a variance I can find from there, for example. So I can do some of those kinds of things. But you can see, you can imagine the problems here. The maximum likelihood estimates don't always exist. That's one simple thing we can say straight away. So anyway, this is the basic idea here. So last week I did mention this thing about the score function. The score function is simply the derivative of the log likelihood. And this is what we're looking at here. We're setting the score function to be equal to 0, and if I can find the solutions to that equation, I'm going to find my maximum likelihood estimates for the parameter theta here. This is for a single variable theta. When I've got more than one variable, in fact a vector of parameters, then in that case things get more difficult. I've got to look at vector calculus there as well, and things get much more horrible there as well. Now this is a very important function, the score function, and we'll see another important one in a little while. So you can solve that equal to 0. We did all this last week, and then you'll find here we get the same solution we got before when we did this last week for the moon data at least. But that works in the same way. You can look at the mathematics yourself if you understand the thing. If you don't, it won't make any difference. The maths here is actually quite simple. The other problem here we discussed last week was where you might have a truncated Poisson model, because in this case what we've got is these are counts of live red mites from a sample of fig leaves. We have the zeros here available to us. In this case we can assume a Poisson distribution and do the usual estimations over there. So this works out fine, and you can look at the derivation there for that as well. But later I think we are looking at a zero truncated Poisson model as well that you should look at, because things are a little bit different there. So here now we're recording results only for those leaves with at least one live mite. So this is a conditional on the event that z is bigger than 0. So this is a conditional distribution now, and all the probabilities have to be revised accordingly here. So here is the distribution. Essentially probability y equals y, small y is going to be conditional on the fact that we only have observations for those leaves with some mites on them. And so things get a little bit more complicated. You can see this extra term here for probability z equals z bigger than 0 is 1 minus probability of z equals 0. So this here is the same as 1 minus probability z equals 0. And that's what I've got over there. So you can see the parameter lambda now appears also on the bottom line. Previously the bottom line contained only the y factorial, a constant that disappeared. But now it's a bit more complicated. Now if you don't understand this, that this is actually a zero truncated Poisson problem, and you just proceed with this as if it wasn't, then you're going to get a bias in your estimate, a very strong bias, right, which needs to be adjusted for by this particular method. Now of course your data may be that you counted every leaf you could find there. You picked leaves at random and counted them. You didn't get any zeros. That's different. You didn't truncate the thing yourself. This was where, in this case, the mean is probably higher than 0 anyway, and you're far away from 0. But it does nonetheless, probability of y equals 0 is possible. In this case, the thing is you can't have y equals 0 because I've truncated the thing. Yeah. Otherwise, as I say, if you only get leaves with mites and none of the leaves have mites which is 0, in other words, every one of them has more than one mite, well, at least one mite, then you didn't truncate the thing yourself, so you can allow the probability of the number of mites being equal to 0. In this case, you can't. Yeah, so this is some differences there that you have to be very much aware of. Now, as I say, statistics isn't as easy as people think. You know, the problem with statistics these days is everybody thinks they can do it because I have a computer and a program. I can press buttons. Well, what comes out of it is only as well as what your understanding of what you're putting in there is going to be. Somebody emailed me a little while ago talking about what they call data dredging and suggested I look at this. I'm not sure if that person's in this class here. Are you in the class here at the moment? No? So the idea with data dredging is this. You collect lots of data on stuff or pick up data that's available. There's no research question of any importance or meaning here at the moment. I've just picked up the data. And then I examine the data and look for the data, and I fit all kinds of models and look at all possible hypotheses. And if you do that, you'll find something is significant somewhere. And that then becomes a research question, and you publish that. But you see, that's nonsense, because this is what we call as the Texas sharpshooter, and you'll find this in the test sleuth, I'm pretty sure. What this person does is, he just goes there and shoots bullets everywhere. And then where the shots are, he puts a target there saying, good, I did well. Yeah, I hit the target. Well, there was no target. You shot first, then made the target afterwards. The same with this. You're looking for the data, you see something that's significant. Now, when you find that significance, it might not be meaningful. We know that data will very often, not just occasionally, have what we call spurious correlations in it. Like looking for things like salary of a person, and eye color or hair color or height. There is some significance sometimes that occurs in some data sets. You can't use that to claim that people with blue eyes earn more or tall people earn more. You sometimes see these kinds of articles in the newspapers or whatever. That research here shows that people with blue eyes earn more. What a rubbish. A spurious correlation in that data set. If you recollect the data, you probably won't find that thing at all. The same kind of thing with data dredging is people just get the data and look for all kinds of significances, and what they find there is not going to be something, although statistically significant, it will not be significant in any meaningful way in the context. And I did mention this, I think, last week. If you find in your models that you're fitting here for our test or anything else, there are some things that are significant. Might, for example, say that in some model you've got age is significant. So you've got the estimate here is 0.0001, right? And it's significant. P-value is 0.001 or something like that as well. So the thing is, this is a significant variable, a very small p-value, but the effect is quite tiny. So I wouldn't complicate my models by keeping that in there when the effect is, while it's significant statistically, from the medical point of view, for example, here, the context point of view, it's got no significance at all. The effect size is so small, it's meaningless here. So I'll drop the variable and make a simpler model instead that explains things a bit more better. Yes?
What about when you got a categorical variable and obviously one of the categories is significant?
Get to that in a second. Yeah. The other problem, though, is be careful, because when you do this kind of thing, you need to look at the values for age, the scale of this thing. For example, if it wasn't age, it was something else that was in tens of thousands. In that case, tens of thousands means when I multiply this by tens of thousands, 1, 2, 3, 4 different places, this becomes 1 or so. That might now be significant, yeah, in that context as well. Because if my response variable is only between, say, 1 and 10, then a 1 here is significant, large, yeah, compared to that. As far as categorical variables are concerned, sometimes you find the same thing. Even you have a categorical variable which is maybe 5 or 6 levels sometimes, and one level is significant there. So again, I would look at the value of that coefficient there, the effect size itself. If it's small, I'll be considering whether I should drop that. The problem is often with categorical variables is that one level that's different is what you're looking for. Yeah, that's the one that makes the difference. So be careful with this. It takes a lot of care with this. And often this requires you to go back and discuss with the data proprietors, if you like, the people who have interest in the data, the other stakeholders, the context-based people. Does this make sense? And you can decide whether to drop or not. But it is difficult because recently one of our PhD students she's looking at data from sub-Saharan Africa on the effect, the incidence of diarrhea in the data that's collected by what's called DHS. the demographic health survey that's conducted by WHO every 4 or 5 years or so. Now, some of the things we put in the model there, it came back from an examiner saying, you shouldn't put those things in the model because they are not going to be of any significance from the medical point of view. And our argument was, you can't decide that because sometimes what your judgment and thinking is may be incorrect. So here we let the data tell the story. So some of the things we find in the models mightn't make sense at the moment, mightn't be explainable, but they're significant and they're large as well. So we'll keep them in the model and we'll let somebody else look at that to decide how it's interpreted, or it's sensible, or work out, hey, this is interesting, there's something happening here, let's investigate this further. It's quite tricky, you see, it's not just straightforward. There's lots of tricks involved here, there's lots of thinking involved and lots of care involved as well as to how you proceed with this. Data analysis is not as simple as people think it is or make it out to be. It's not as simple as that. It's far more complex. If you don't do it properly, you get rubbish out of it. Now, in many situations, people spend years and lots of equipment and expenses to collect the data. You run a medical trial with, say, for example, AIDS patients over 3 or 4 years, and you've got longitudinal data, you look at this data over 3 or 4 years, and you're looking at, say, a treatment versus a control, a treatment, new drug versus an old drug, new treatment regime versus old treatment regime. You follow these people over 3 or 4 years, and then all you've got left after the end of that expensive trials and all the hard work is just the data. That's all you've got left. And imagine if you're doing this with animals, mice or whatever, lab rats, you're killing them in the end, yeah? And you've got all kinds of problems with this sacrificing of animals, and all kinds of ethics approvals you have to go through. At the end, all you have is the data. If you mess that up, you've destroyed the whole thing. And I published a paper, you will find it. You look for who needs statistics. Who needs statistics is what my title is. And I've seen PhD theses in Australia and New Zealand. One guy did this exact experiment, the exact trial with AIDS patients. The data he has got, it was a he, was longitudinal, right? You've got data over time, over 3 years or so, and you've got measurements in the patients every 6 months to see how they're progressing. And you're looking at T cells, whatever else in the body, to work out how the disease is progressing. So to compare, what we're interested in here is going to be the effect of the treatment and the effect over time, the two major things. What are the covariates? What are the other covariates in the data that will be available to you or should be available to you? Name one. Sex of the patient, another one. Age of the patient, another one. Height, BMI, that kind of stuff, another one. Height, weight, BMI, yeah? Those kind of things. Anything else? Race is important, yes. Smoking, not smoking, any other conditions? Yeah, any others? Another one is usually you get some kind of basic index of overall health. Yeah? How is the patient overall health-wise? If they're sort of pretty bad, then you might not expect much improvement either way, whichever one you use, right? And so you hope you can randomize in some particular way and do it properly so you get the demographies, at least health-wise, those things are balanced in the data in both those, the trials and the control, yeah? So those things must be part of this. This student, what he did was, to look at the difference over time, he looked at 2 time points. So I'm looking at these 2 strands as such, you know, treatment, my treatment I'm testing to see whether it's better or worse, and the old treatment. So he looked at that treatment line here, at 2 different time points, and did a simple t-test. Next 2 time points, another t-test. The same with this one. That will tell me if that particular treatment is different these 2 times, right? Just the treatment itself. But I can't compare to see the differences over time for the 2 treatments. And I can't put any demographics in there. Yeah? To look at the difference between treatments, he picked a time point, and those 2 time points for those 2 treatments, t-test, t-test, t-test. What a waste of time. The problem is, not only will this be inadequate, it could be totally wrong. It could give you the totally opposite picture of actually what's going on. Yeah? It's a waste of time to spend that much time and prepare this stuff, do a medical, these expensive experiments. And what, of course, the funny thing, of course, is, and not so funny after all, is that there's published papers based on this thesis. Now, who on earth were the people who refereed the paper and passed it as publishable. And I should be thrown in the bin. That's how bad it is. And this is in Australia, in Sydney. You look at the paper I wrote it earlier, you'll find the same kind of rubbish papers in the University of Western Australia, our university. Why is it so bad? Because anybody can do statistics. I wouldn't. The thing is, always remember that good advice isn't expensive, it's invaluable, yeah? It's invaluable. Good advice is invaluable. You do things properly, you make big, big changes in the way you think. And that's the whole point of all this, right? It should change the way you think of things. A new thinking, because it should inform you now. Otherwise, it's useless, absolutely useless. And whenever you have had this change in thinking, that's when the big changes in science and technology has occurred. Because you go back to, I keep pulling up this idea, the story of Planck. You will have Planck's constant. This guy Planck, if you know him, I'm sure you, being science people, will mainly know him. He was looking at photons and the energy in photons. And all the modeling he did showed that photons, the energy in photons wasn't continuous, but in packets, discrete, and he couldn't believe it. So he redid his calculations 3 times, and when he did it so, he convinced himself there's no other option, that must be it. That is the only option. He published his paper, and of course that changed the way people thought about this. Yeah, changed the whole thinking. And that's what led later on to this other guy by the name of Einstein with his photoelectrical stuff. Now, most of you mightn't realize that Einstein's Nobel Prize was not for relativity, it was for photoelectricity. They worked in 1905 or so, right? So it was for photo. Of course, he deserved one, I'm pretty sure, for relativity as well, but his actually Nobel Prize was on this particular work. Yeah, some 20 years later. So a lot of these things take a lot of time to develop as well. But the big thing is, when you have these big changes in the way you think about things, a whole new picture opens up for how the thing actually behaves. One of our own professors over here, by the name of, you probably not, he's not here anymore, but some of you might know this guy, a world leader in his area. He works in the area called stereology. Stereology, I think that's how it's spelled. The idea here is, if I find myself, a gold ingot somewhere up north, and I'm trying to find a mine there somewhere, I can work out how much gold there is by sending the thing back to Perth here, and they assay that thing and work out how much gold that is there. And that takes a while, it's expensive as well. What the idea is I can actually slice through these things. And by looking at the area of gold versus the area of the total thing, I can work out percentage of gold in this very fast, very quickly, very accurately if done properly. And that saves lots of time and effort and also lots of money and, as I said, time. Now, problem with this is, and the example Adrian keeps giving is, see, if I have a bowl of jelly, I'm not sure I went through this story before. Here's my bowl of jelly over here. And I put a banana in there, right? I'm sure I must have mentioned this story before. I slice the top of this, I see 2 bananas, one over here, one over here. But there actually is only one banana in there. Yeah? And so you don't count properly. It's interesting. Counting is one of the most difficult things we do. One of the first things we learn in mathematics or arithmetic, one of the most difficult things to do is count things properly and accurately. You see 2 bananas there, but you have to be careful, of course. There's only 1 banana. And of course, you can extend that to now cells, liver cells, brain cells, and kidney cells. How do you count them? You slice through, you count them. Is there 1 cell or 2 cells? You see how difficult it is to do that. But if you do it properly, and so the statisticians who did this properly then sent off the articles to the medical journal saying, this is how you count these cells in kidneys, for example, or livers or brain, and this is what it actually means. And they made it objected because, somebody has spent their entire career on this kind of stuff, won't let go so easily of their whole, last 20 years' work. A struggle. Over 3 years or so, the arguments went back and forth, and eventually the journal editors and the rest agreed that what you were doing is correct. But you see, the problem was this holding on to old ideas without reason, without justification, holds up progress in science. Once they agreed with this, the whole idea and the whole thinking of how the lung functions, the brain functions, kidneys, livers, everything changes as to how they function, you see. That's important. People used to keep thinking that the brain declines over years. Yeah, it does to some people. For many people, it does decline. But you saw the video I showed earlier with the nuns earlier. You see, the brain's amazing, actually. It's as good at 80 as it is at 18 for most people. It doesn't. People thought that your brain cells die or your neurons die. It doesn't, actually. It doesn't die. Your brain shrinks a little bit in size, apparently, over age. But it's just as good at later age as it is at younger age. And in fact, the kind of thing I'm looking at, and I'm working with some students over here in that area, is you can actually make sure your brain keeps it up with its activity and its ability. In fact, more than that, you can actually grow your brain. In the sense, you can actually grow neurons, you can grow connections between them, you can make them better. Yeah, you can maintain your brain activity, and in fact, you can make them better. Anyway, that's all part of something else. But you can see the main point here is, if you think of problems properly and get the right solution for those problems, then your understanding of how things work is going to be different. And I believe myself, and I'm hopeful that most of you also are, what I say, are seekers of the truth. Seekers of the truth. If it's true, and I can see it's true, I accept it. I don't turn my back on it because it goes against what I think or my career, right? In fact, I should join the thing and promote it and become part of that to progress myself. So if you are part of this group of people who actually will think differently, because lots of papers out there in statistics are really bad, really, really bad. I'm hopeful that we can educate a group of people out here who go out there and don't just have the basics of this. People fit normal distribution to this kind of data. Normal distributions, normal regression models. It's useless. It's terrible. Gives you nothing at all. Yeah? As I said before, it's not just wrong, it could be completely incorrect, give you the opposite of what actually should be happening. So be careful with this. If you're not sure of something, ask somebody else. And I'm again mentioning this work we did with BHP Bulletin with the conveyor belts a little while ago, as to how we modeled essentially Poisson distribution and binomial, because we looked at the failure of belts, whether they fail or not within 3 months. That's a 1-0 process, right? Simple as that. And so we fitted appropriate models for that. We found the rates of failure by looking at various measurements. We published, actually, when the student did a thesis, the engineers in BHP Bulletin, one guy was the lead engineer, he said, I worked with the top in the world over the last 20 years in this. This is cutting edge work. It'll save us millions. It did save them millions. Simple models of the kind you can do yourself, perhaps in the guidance. Yeah? The problem I have is not the engineer didn't know what to do with it. The problem is he didn't know what to do with it. He didn't bother asking anybody for 20 years, holding up progress. Now, the world around us here in Australia, especially WA, is full of these kinds of things, where by looking at very simple ideas and hiring somebody and spending maybe $100,000, $200,000, $300,000 on the person, they can save millions, make processes much more efficient, save millions. BHP Bulletin, of course, they don't have the maintenance crew up north all the time. They go every 3 months to look at the thing, and in 3 months' time they may decide, will this last 3 months or not? If it doesn't last 3 months, we'll replace it now, because if things break down, then it holds the production, everything goes crazy. Whereas if you plan maintenance, you plan the thing around production, and you can move things around a little bit. So that saved them millions, because we could predict very accurately whether the belt will last 3 months or not. Another piece of work we did, again with similar models, Poisson models, was looking at the number of leakages in pipes in WA, waterworks. Yeah, simple stuff again. Blockages of sewerage pipes, simple stuff, not very hard stuff. But again, it saves millions, done properly. Done properly. Yeah, don't fit normal models in this kind of crazy stuff, because it's useless. It's count data. Anyway, so this is my argument about how things should be done properly. So you can't gloss over things, and I'm very disappointed in many ways in how our university handles many things. Many of our courses, we put together, and I'll say this loudly, I don't really care who's listening, is we put together a master's in data science and a bachelor of data science. And we paid lip service to the stats part of it. If it's data science, it needs to have proper, good, sufficient stats in it. Otherwise, it's useless. If I teach you some basic stuff here and there, you'll go and do this kind of stuff like putting normal distribution of this kind of data here, right? You'll do rubbish stuff. You need a strong background in that. It's not just computer science, it's data science. It needs to have both properly in it, enough of each of those things. Otherwise, it's useless. Anyway, I hope you guys won't be in the same kind of class. So you can see some differences over here in how things work if the model changes. And you need to be alert to that, understand that. But by all means, whenever in your career you find you don't understand something, you don't know what to do with it, admit it. Tell them. Tell your bosses, I don't know how to do this. Let's get somebody. Consult with somebody. Come over here. We're full of people over here who can do this kind of stuff. Now, the other thing here is that you can actually do the maximum likelihood estimation numerically using R, and I just want to very quickly look at the programs and the functions that actually do this. The first thing is you actually have to do you do actually have to put together the likelihood function here. So here is the log likelihood function. Here are the derivatives, the partial derivatives of this here to maximize, and you can solve each of these. Essentially, you want to make this equal to 0 individually. Sorry, make them 0 and solve the simultaneous equations you get from there for both of those things. And usually they work out nicely here in the two variable case. These are nice simple equations, but sometimes it's more difficult. So you can see here the idea here is this is a vector. It's a score vector. I've got two equations over here, and these are the two components of the vector. And I can find the maximum likelihood estimates over here. Now, if I actually do this numerically, then I've got the stats, the MLE program in stats4 package does the thing. So if you load the library stats4 and MLE, you'll be able to find that working fine. And so very quickly here, this is the definition of the log linear function. In other words, log linear function has been programmed in there. And you can see we're looking at the MLE, maximum likelihood estimate. With it using, this is the function we're trying to maximize over here, and I require a start list to start this whole iteration process off. I require to give it two initial values for pi1, pi2, right? If you don't choose them well, I should say not properly, but maybe wisely enough, you might find you're too far away. And if you're usually, the thing is, if you're too far away from a maximum of the likelihood, sometimes it doesn't converge. It gets lost somewhere else. That's the only issue here. It might not converge or go somewhere else. But it's not very hard, because with the data you can pretty easily find some values that are going to be reasonable, and you can just start them off. And of course, if you find you start them off with the values that don't make any sense to the program, it doesn't converge somewhere, give it some new values and see where it goes. In many such situations with more complicated problems, this is a very simple, it's a two-dimensional, what we call manifold essentially. It doesn't misbehave in many ways. But if you look at high dimensions, something like 30, 40, 50 dimensions, you can't be sure of how the manifold actually behaves. You might have various dips in there, and you might just give a starting point, and you might get stuck at one particular place, which mightn't be, it might be a maximum, but not the maximum, if you like, right? It may be a local maximum. So in those cases, we actually throw a grid over the whole thing, and we have various starting points to see where they end up in the end. And we compare them all in the end. So this thing is rather tricky, but as I say, R does a fairly good job of model fitting. So in this situation here, if I just want the MLEs, I can use this program to do it. And here are the answers from R itself, and you can compare them with the MLEs. Sorry, you can compare them with what we get by looking at simple proportions. All right, anyway, enough of that. I want to move on a little bit here. So the same idea here, but in another context. We're going to look at regression now. So I've got Poisson regression. So the idea is, here is my observed data here, looking at the mating for elephants here. My observed data is going to be Poisson, and so that's the distribution over here. That's a probability mass function. But the parameter lambda here has a regression on it, which is the log linear function. So essentially log of lambda is equal to beta naught plus beta 1. Yeah, the model here we had was log lambda I. Is a linear regression on this, so it's beta naught plus all the rest of it. So lambda I has that particular model. Now, in this situation, where my observations are Poisson, and I have this regression model fitted onto that, I want to estimate my beta naught and beta 1, not lambda I, because that actually is regression, right? Lambda I comes from another model here, beta 1, with the log linear model. So how do I go around doing that? Well, you can again write down the likelihood equations for beta 1, beta 2. Yeah, here it is for the overall equation for a Poisson model, usual stuff over here, but the lambdas, of course, are now going to be with the regression as I have over there. So the log likelihood here, still in terms of lambda, and given still this particular condition there, you can actually write them down properly and maximize them. So the mathematics has not been completed over here, but if you can do the maths yourself, I invite you to do that. All you have to do is put the lambda I here and here. You can see it gets complicated because I've got log of lambda I, where lambda I is exponential. But I can still do this by differentiating, equating to 0, and solving them. Now you'll find, of course, you can't solve them by hand analytically. You won't find closed form solutions for this. But R does it, and many other packages will do this kind of stuff for you. Of course, when you fit this kind of model with R, as we did before in the earlier part of the course with Poisson modeling, it found for us the beta naught and beta 1 in the regression analysis itself. So that is easy to do in that case. But here is the actual calculations for this by hand, and these are plots of the data over here to see what it looks like over here. And you can maximize this again numerically if you wish by using R, and that is what's actually we can do when the GLM package uses this idea. That's what's happening here. We're using GLM over here to get this MLE over here. Sorry, we're using the MLE again from the stats package to look at this maximum likelihood estimates, and again I give it a starting list of values beta 0 and beta 1, and it can do that for me. So these kind of nonlinear programs is also it can solve very well. You can compare this with what you would get if you were to simply put in a GLM here, and it's been done there, and the values here are negative 1.58 and 0.6889. Not very far off. Not very far off. Slight differences because the way they do this, these estimates here in the GLM are not necessarily maximum likelihood, although you can force it to be maximum likelihood. So it's not necessarily maximum likelihood. There are many algorithms also to estimate and maximize these kinds of things. Anyway, I've just shown you all this stuff. I'll leave it there. I want to move on to the last part of this course and finish off here. So there you will find we're looking at in the next week apparently. I'll do it now here. Is properties of MLEs. So we can then try and take a look to see how we can do things like likelihood ratio tests and form confidence intervals and those kinds of things. But the problem is it requires second derivatives, especially when the partial gets rather horrible. Anyway, I want to go ahead and look at that. So this is lecture 12, 3-bit-12, not 12A. Why do I have 12A there? The only thing I want to look at here is this idea of sampling distributions. And so because with sampling distributions comes this idea of then finding confidence intervals, because I can then find the standard errors of my estimates, and if I have a distribution that I can form confidence intervals, I can form hypothesis tests. So I want to go through the details of this relative likelihood function, but the main thing here is going to be that we have this idea of I'll skip all of that. You can look at that yourself afterwards. Not so important for me. This idea of curvature of the likelihood is important, and that comes from the second derivative. And we'll see how the second derivative actually is rather useful. If you've done any calculus, you'll know the second derivative can decide for us whether it's a maxima or a minima or a saddle point or a point of inflection. Those kinds of things can be decided here. The other idea here is observed information. So the first derivative of the log likelihood function was what we call the score vector. So the first derivative was the score vector. So S at theta was d by d theta of the log likelihood. The second derivative, its negative, is what we call the information. Now, if theta is just a single value, single parameter, these things are scalars, scalar functions. But if theta is a vector, if I've got two things in the parameter vector theta, like pi 1, pi 2 we had with the lunar data, then my S here will be a vector and my J will be a matrix. So it's information matrix we're looking at here. Okay, that's important. It's a matrix in general. More than that, when I get to looking at things like, so this idea here, the partial second derivatives here is a matrix that's called the Hessian matrix. That's the name we use for the second derivatives. Now, to actually find the information matrix, I'm not going to do it over here, but if you do any higher mathematics or higher statistics, actually, you'll find it there. Excuse me. The most important thing with the matrix here, the information matrix or the information, is this. The expected information, what we call Fisher information, where you take a look at the second derivatives and expected values of those things over there, is rather hard to do often. But the observed information is what we often have, and that comes from the data itself. So what I want to get to this is this one here. And this is for the binomial, can be worked out very, very easily here. Excuse me. The idea is this. This thing called information actually does have some information, some meaning behind it. Its inverse is the variance, in this case, of my estimator. So the estimate comes from solving the score vector to be equal to 0. But if I find the information, it takes its inverse. Now, if of course theta is just a scalar, the inverse is just 1 upon the information that I obtain. Otherwise, of course, if I is a matrix, and I want the matrix inverse of this, I want the inverse matrix. And the inverse matrix here, the diagonal elements of the inverse matrix will be the variance of the individual parameters. The off-diagonal elements will be the covariance elements. So this is rather complicated stuff here. What you'll find here, one of the things here is when you talk about regularity conditions, in other words, I must be able to at least find the second derivatives. First derivatives and second derivatives must be or will be found. So the function or the likelihood function must be differentiable twice. Now, the other aspect here we found is that these MLEs here are approximately normally distributed, and this is a large sample result, but the sample doesn't have to be that large in the end. We usually say 30 or so is big enough, even 20 under certain conditions if things work out well. If things are symmetric, even 20 is good enough. So there's two things we get here. It's normal, the parameter estimates, the MLAs are normal, and we have the theta here from the score vector that we're solving called 0, where the variance matrix or covariance matrix comes from the inverse of the information matrix. Of course, once I have normal distribution, I can then from there form my confidence intervals in the usual way. Here we actually are going to look at the expected information matrix in the calculations. I invite you to look at them yourself. If you have any problems, by all means come and see me, but I think most of this should be clear if you've done the maths here, have done maths previously and have the right backgrounds here. So this other idea of biasedness is also important. One of the properties that good estimators are supposed to have is biasedness. Sorry, should be unbiased. This is a tricky one because sometimes it will take a biased estimator as being okay as well, but sometimes the biased estimators have a smaller variance, so we'll take that. In the end, if I can work out the bias, I can always adjust it as well. If I know what the bias is, I can adjust the thing, but I might be able to live with a smaller variance as a better estimator. But these things are complicated. So the bias is essentially an estimator is unbiased if on average, its expected value on average, if you like, the average value is equal to the thing I'm trying to estimate. So we very well know that if I'm looking at, say, y bar as the average of some data, and I'm trying to estimate the mean of the data by y bar, I know that E of y bar is equal to mu here. So if my y's here are all with mean equal to mu, and I take the average of the data there, the average is an estimator for mu, and its expected value is also equal to mu. That's why it's unbiased. So the sample average is unbiased for the population mean, we know that. the sample proportion is unbiased for the population proportion. We know that. Those kinds of things we saw earlier. That's what biased means. And the mean square error, of course, is just the expected value of this thing squared. Is essentially the variance, if you like, here. So it's the variance plus the bias squared over here. And so if the bias is 0, then the MSE is equal to variance. Otherwise, there's some offset there a little bit. But yeah, this idea of consistency essentially means that the error term, or the mean square area here, error should go to 0. Essentially, that means this term here should go to 0. For unbiased estimators, the variance needs to go to 0. We know for the sample mean, I know the variance of y bar for the sample mean is sigma squared upon n. You find this the case in many estimators. There's an n on the bottom, which means that this will go to 0 as n goes to infinity. So this is consistent. In other words, what we're expecting is that as I am increasing my sample size, the error, or the difference between my estimate and my actual value, the mean here, is going to decrease and narrow down, right? It's not going to be wide or mess around a little bit. It'll get closer and closer to that value that I'm trying to get to, which is the mean in this case. So this is this idea of consistency. Sometimes people use the word consistent and improperly. See, in statistics, words like efficient and consistent have particular meanings. So we avoid use of those unless we're using them in the right context with the right meaning. Yeah. So efficiency and consistency, this other idea of sufficiency as well for estimators, these are all words that have particular meanings in statistics. So unless you know what they mean, don't use them. And if others use them, make sure they understand what it means. And the last bit I want to get to here is probably the next slides, I believe. This is just asymptotic things. This is just distribution of the MLEs. That's all there is here. And the last bit I want to get to is this one here, to do with tests in the end. I think it's in the last few slides. They get there very fast. This is the idea of likelihood ratio test is what I'm after. You've seen this all before. Standard errors, yes. So as we know, if I can get the variance is, as I said, 1 upon that, or essentially is the inverse, if it's a matrix, inverse matrix here. And so the standard deviation is the square root of that. So the variance comes as the inverse of the information matrix or information. It's very important because, of course, if you're trying to work out new estimators from models that are fitted, you're trying to work out properties of the estimators, and you know, for example, if it's MLE, it will be normally distributed, but you still have to work out what's going on with this variance. And very often you have no other option. You might find it simple in many cases here, but you don't have many other options in many other situations than to compute this matrix. You've got to compute that matrix. There's no other choice. You've got to find it in more complex situations. There are a whole lot of problems out there in statistics that are very complicated, and you've got no other way than doing all this kind of stuff. So what I'm going to try to get to in the end is this idea of confidence intervals. So we know that if I've got these things that my ML is approximately normal, I can just use the usual normal distribution things to work out my confidence intervals in the usual way. So as before, I have an estimate over here. I've got an appropriate z value, and I've got the standard error of estimate, plus or minus both sides. I get the confidence interval. And so this is nothing different from what you've been doing all the time as far as calculating confidence intervals is concerned. Here's an example that you can go through and work through in the details. That's fine. Please do so and have a look at that. What I want to get through to in the end is this idea of the approximate distribution of minus 2 log likelihood at the value of theta note here, which is the true value of theta. It's approximately chi squared r. So notice I've got r parameters there, and that chi squared r comes into there. So the chi-squared distribution, for those who are interested, chi-squared r is actually the sum of, the distribution is the sum of r normal not 1 distributions squared. And thus I've got, say, z1 squared if I put x equals that where z are normal node 1 distributions, then my x is going to be chi squared r. Now the condition of course is the z's are independent, but if I've got, so chi squared comes from summing r independent normal node 1s squared. And that's why things like, for example, the sample variance, here, the variance comes from this idea of sum of xi minus x bar squared. Now if I divide that by sigma squared, see, because the xi, if it's normal, I'm taking the mean away, that makes it normal not 1, sorry, normal not sigma squared, divided by sigma squared, that's normal not 1. So this is going to be chi squared, and if I divide here by n minus 1, is chi squared n minus 1. And the reason we divide by n minus 1 is that the n minus 1 makes this unbiased, but also I know that if I've got this kind of expression here with xi minus x bar, I don't in fact have the r of them independent, because you see, once I fix x bar, then the data itself only, if I've got r points, if I have x bar as well, then only r minus 1 points are independent, because the sum has to satisfy x bar, right? So the last point here, the r point will be not independent. That's why I haven't got, in fact, in this case, r independent normal not distributions, or n independent in this case, but n minus 1. So that's why this comes around here. And so this is chi squared n minus 1. The thing with this is, because of the way it's worked out with z squares over here, I know straight away that the mean of the chi squared actually is equal to r. Chi squared r is mean r. The variance works out to be something else. You can look at that afterwards if you wish. Anyway, that's the important thing over here. And so this is where the likelihood ratio tests come from, because I'm looking at two different models. What we can do is, I'll skip the likelihood ratio intervals over there, but what we can do is, if I'm looking at two different models, one model has an extra variable, nested model, for example. For example, if I would say a model with beta naught plus beta 1 x, and I've got one with just beta naught in there, and I want to have a test of the two models, then I can use a chi-squared test, and you've seen this before. So the chi-squared test here will be based on the likelihood ratios. So because this log likelihoods, if I divide the likelihoods essentially, then what happens is, if I look at the likelihoods and divide them, take the log afterwards, I'm just subtracting the likelihoods. The degrees of freedom will be different between the two models according to how many parameters one has compared to the other one. And so this is the idea we saw earlier here by looking at the chi-squared tests, and I just want to get to that part here. So this is, well, while we're with this here, this is the Wald's test. We've seen this before. This is the usual z test we use, nothing different. So it's theta minus the value theta naught, and of course usually what we have is h naught will say theta naught is equal to 0. So in your tables for the R output, you'll find here the parameter. For example, it will say something like intercept, or say age. It'll give you the value of the parameter over here. Yeah, let's make it beta 1. It will give you the standard error over here. It will give you the z value here. And so this is just beta 1 over s1, like this one over here, because theta naught will be 0 by hypothesis. And so the p-value comes from there. This is what Wald's test is, nothing more than this normal test, essentially, nothing more than that. It's a normal distribution test. Why people call the thing the Wald test is because somebody's name come up there, that's really all there is. Other than that, it's nothing more different than what you've done all the time. It's just based on the normal distribution, nothing more. So the Wald test here, essentially we look at p-values for individual parameters in the output for R or in the output for a model fit, and decide whether they're significant or not. And it's always two-sided. In the model fitting in R, it's always two-sided. R doesn't know what you're going to test. It will test simply for beta equals 0 versus not equal to 0. It's two-tail test always. It's just, as I said before, based on the normal not 1 distribution. But you can also base it on the likelihood ratio. And Wald's is for single parameter hypothesis. So we look at the output from R and pick out the ones that are significant and drop them one by one or whatever. But if you're comparing two different if you're comparing two overall models, then you can use things like likelihood ratio tests. And that's what this is all about. Now you can still use likelihood ratio tests for a single parameter. You've got one model with a beta 1 in there, and the next one doesn't have beta 1. Beta 1 is equal to 0. You can still test between those two things, and that still will work. And that essentially becomes similar to the Walls test. So nested models here is what we're looking at here. MU is the full model or unconstrained model, and this here is the constrained model. So be careful when I say things like that and this. And that's my full model. The full model is where things aren't 0 or unconstrained. And this is my constraint because I've put the constraint that beta 1 is 0. That's my constraint model. People often get this wrong. So if I've got that particular situation, I can still use the likelihood ratio test. It's nested, you see. So I've got, if you like, my model H naught is nested within H1. H1 says this is my full model. So I have something like, for example, my H1 will be essentially saying that my model is y equals, very simply, let's say beta naught plus beta 1 x. And my H naught says y equals beta naught. So my H naught is nested within H1. So H1 is the general model, the full model. H naught is when I drop a parameter is nested within that. So for nested models, I can use the likelihood ratio test. And well, of course, in this situation with a single parameter, I can also use the Walls test. But you see, what if I've got something different here? Let's just go for an example of the kind you're familiar with. If I'm taking a look at something like, for example, let's just again just have generic y equals beta naught, and I've got beta 1, and I'm looking at a categorical variable with 4 levels. Okay, L1, L2, L3, 4. Categorical variable with 4 levels. So let's take a look at, say, if I break, for example, age into 4 levels. So I've got age 0 will be out of it, age 1 plus beta 2 age 2 plus beta 3 age 3. Now, so in this case, if any of the beta 1, 2, 3 are significant, then age stays in the model, otherwise it drops out in the model. So if I compare the full model in this case with the restricted model, then my other model is going to be that y is equal to beta naught. All the age terms drop off. In this case, I've got 1, 2, 3 beta terms I'm dropping between those two models, not just one, 3 of them. So if I look at this from a point of view of the R output and pick out any of them as significant, and I can say, I'll keep this over here, the whole variable stays. I can't just drop one of the levels. Or I can drop the whole thing, and in that case, if none are significant, I can drop the whole lot. But properly, really, to compare the two models is where I've got a nested model within another. So this is nested within the other model. Then I should use, or I can use, the likelihood ratio test, and this is where this is useful. Now the problem here is, be careful here, is that I must have the two models based on the same data. If you got missing values, then dropping a variable sometimes means some of the records that had missing values for that variable in the new model will now be part of that. So when you drop variables, as I say, sometimes other records actually come into the data. So you'll find at the bottom of the R output, it will say how many observations were omitted because of missing values. And if you, as I say, if you base the thing on different data sets altogether, then you will find you can't do that. But yeah, this is the whole idea, and very quickly what's happening here is you're taking a look here at the likelihood ratio test. So likelihood ratio test here, LC is the maximized likelihood for the constrained model, and LU is the maximized likelihood for the unconstrained model, and this is the likelihood ratio test. I take its log and negative twice log, because of course usually these kinds of things are not going to be, well, they're less than 1 or whatever, so the likelihood becomes negative. So we take its negative to make it positive when we take the log. And so the negative log likelihood twice is essentially twice the likelihood of the top and the twice likelihood of the bottom subtracted. The negative makes it the other way around. So if you take a look at the negative log likelihood here, is the log of the bottom minus the log of the top, and it's doubled as well. And so the idea is you're looking at the constrained versus unconstrained, yeah, and you want this to be, if it's just the ratio of the likelihoods, if the constrained model is more likely, or the better model if you like, then you expect that number to be bigger than 1, otherwise it's less than 1. If the constrained is better, it will be less than 1. Sorry, again, if the constraint is better, this will be bigger than 1, otherwise it will be less than 1. So it's a matter of saying whether it's sufficiently different from 1 to work out whether one model is better than the other one. And so we use this likelihood ratio test. And the thing with the likelihood ratio test here is that it is, and this is just going through some of the details of calculations. For me, that's not important. The important idea here is going to be is chi squared d, where d is the difference in the number of parameters between the two models. So a lot of stuff you've seen earlier, I hope is beginning to make some sense. There is quite a bit of maths behind this. If you do any higher tests, you'll find this occurs all the time, because in many situations we don't have these kinds of ideas with wall tests or whatever else. Yes?
So, 2 lectures, I think ago, we used that test to get bottom to negative binomial. Is that considered nested models, or do they seem different models?
They're different models, but you can still use the same idea.
Okay.
Yeah?
Even though they're not nested?
Not necessarily nested, yes, yes.
So I used that in that last lab test, and when I used the function, it said it converted to achieve the negative binomial model to achieve a model.
It's a matter of, you need to look at the details. Show me sometime after, I'll look at the details of that, right? Something with the model fitting over here. Yes, so you can compare 2 different types of models as well with this. Yeah, but of course now the issue is if the models have the same number of parameters, then you can't compare them because you get 0 degrees of freedom there, right? But you'll find in many situations you have no choice but to use these kind of ideas, because your other ideas on the parameters and their distributions are just too difficult to work out. And in the end, you might not want to compare just single parameters anymore in this nested kind of idea. You might actually want to compare 2 different kinds of models altogether. And when I say 2 different kinds of models altogether, as a very quick example, let's take a look at this situation. Some data is recorded there, right? Now this is data from something called ion channels. This is an area I work in. An ion channel is this protein molecule in every cell membrane that under the right conditions of stimulus, either electrical or mechanical or chemical, it opens up like a pore, a pipe. It allows the flow of ionic currents in there, sodium, potassium, all the kind of things, and that leaves lots of different things that happen in the body after that. So the problem here is that when you record the current, you can do this recording is actually not so difficult. what you get is noise that also adds on to that. When noise adds on to things, these things become difficult. The understanding is that these things have a certain number of states, so they're closed or they're open, and there may be some levels in between. Now, in this case, I don't know the number of levels in advance. The problem is, to fit any suitable models to this kind of data requires me to know the number of levels in advance. So how do I proceed? I say, all right, I'll start with 2 levels. Now I'll put 3 in there, and 4 in there, and 5 in there. Now they're different models altogether, right? In some ways they're nested because I've got from 2 to 3 to 4 to 5. They are nested in a sense. But to compare the models, I can't just compare parameters because they're useless. The number of parameters in this are going to be different to the number of parameters, but it's not just number of parameters. What they actually mean is also different. So I can compare those based on likelihood ratio tests. I almost have no other option here. For complex models like this, you've got an option but to use these ideas of things like likelihood ratio tests. And in many situations, because you can't just bung this into R and get a solution out of there by using some buttons or some model fit like LME or whatever, it doesn't work like that. You have to write your own programs to analyze the data yourself, and you have to calculate the likelihood yourself, then compare between the models. Rather complicated stuff. But you've got no option there than to use these kinds of ideas. So you'll find later on that even in not quite these difficult situations, but even simpler situations, we do use the log likelihood for a reason. It compares between models, essentially, not just whether a hypothesis is true for a single parameter value or not. So I wanted to actually show that to you more than anything else, that you've got this idea of this likelihood. It's based behind a lot of theory there. You'll find a whole lot of books on this likelihood ratio test and likelihood inference as such. There's quite a bit of large work there. And in fact, this is quite rushed, I know. I'm pretty sure if I teach this course next year, I'm going to reduce this quite a bit because the course has changed since the student background has changed quite a bit. This is very interesting stuff, but it's not, I think, suitable for this course. But you will see enough of this, so you go to the next higher course in third year or whatever, that you understand or have seen some of this before. So I think enough of that. And you'll find some more details here, but all means look at this afterwards for yourself. And there's another idea that is important, is this idea of deviance statistics. You find all the time we talk about deviance models, we saw this idea of drop-in deviance test. And the drop-in deviance test is nothing more than just idea of the difference between this, what we call one model to another model, saturated and intermediate model over here, these kinds of words. Saturated means you've got all the parameters in the model, all the parameters are available in there, and you can drop them one by one as you go through here. And here, the drop-in deviance test is similar. It's still chi-squared. You look at the drop-in deviance, you look at the difference in the chi-squared, look at the difference in number of parameters, becomes chi-squared. It's similar to the log likelihood ratio test here. So I'll stop there. I think I've said quite a bit already. What I plan to do next week is one of two things. Either I can come here and be here to answer questions on things like for the exam, for example, or I can be in my office and you can come and see me. Either works for me. I don't really mind being here. So maybe the best way is for me to just turn up here and see all of you who will be here, and let's see how much time we spend on that. I know I've covered quite a bit today, and I don't expect you to understand it all straight away. It takes a while, but I would advise you very strongly, for those who are interested and have the right maths background, to look at this afterwards. Something to read over and mull over and see very carefully. A lot of the maths isn't so difficult in the end. It works out nicely in this case. It's not so nice in many other situations, but here's nice. So let's stop with that and let's get to the assessment. And all the tests are finished, right? Test 6 was due on Friday, and now is the final exam, which is due in the Monday of the study break. So I didn't intend for that final exam to be too onerous. The hardest bit, in my opinion, is not data analysis, because I think you've got enough R commands or help in the brief and the notes to guide you. All you've got here is in the original data, you've got these different kind of visits. You want to, and those visits are in different variables. You want to convert that from wide format to long format. So you've got a variable that tells you the type of visit, another variable that tells you the number of visits by each person of that kind. Once you've got that, it's simple, because you've got essentially a categorical variable which says the type of visit, a response variable that says the number of visits, and all the other covariates to fit in the model. Three models to try is Poisson, quasi-Poisson, and negative binomial. In the Poisson case, you can test for the dispersion. Quasi-Poisson you can't, because it only applies to Poisson, and you'll see which of those three models fits best by looking at residuals, whatever else, and work out what the best model is, interpret that, write it up. The writing shouldn't be difficult either, because you've got the ideas from the last test, right? You're going to have the method section, results section, and discussion section, maybe conclusion as well. Yeah. The hardest part is the first part, introduction with literature review. You have to do some searches yourself in this area of the use of health services. See what's available out there. I think you'll find quite a few papers in the US context and maybe in the European context as well, but certainly in the US context you'll find quite a bit. And this paper or this article that this data comes from was from the US context. The article was referred to in your brief, so look at the article by all means. Don't expect to understand everything in there, but you'll see the data context at least that you can essentially distill from there. So don't copy from there. You can distill it, explain how you got the thing, right? Because it's very easy to cross-check with the article to see whether you just copied and pasted. It doesn't work very well. Write the thing in your own words. You won't require the whole lot, basic ideas. The paper is quite long there. Just get the basic idea of the data collection procedure, where they got the data from, all the rest of it, and refer to the article for all those details. What will change is the method, because your data is different now. They only looked at, in the paper, they looked at only one variable, one of the types of visits they looked at. And that's what the one you looked at, I think, in the last test. We're looking at the whole lot now, all of them together in a different way, yeah? But do find some literature reviews on there and write it clearly. Don't miss it, no, don't complicate things. Don't overcomplicate things. Write it simply. Simply usually is the best. Make it simple and clear. Your report doesn't have to have long sentences. Don't use long sentences. Big words, no. Make it simple. Simple. Explain the thing simply as you can. If you think that the best way to explain something is itemizing it, dot points, do that. Maybe that's the best way to do some things, right? But write the thing properly and read the thing at least 3 times before you submit it, as I said last time, I think. So you've got about 2 weeks to do this thing. So next week's week 12, it's actually exactly 2 weeks to do it, isn't it? That should be sufficient time. I hope you started actually early. The data analysis is the first thing you should do, because that's out of the way then. Then start with the literature review part of it. But the things you can write very fast would be methodology, which involves data collection as well. You can write the results down very fast. You can do some discussion and some conclusions, at least skeleton-wise, very fast. But then the first front-end introduction, abstract will be the last things you write. Abstract's the last thing you write, usually in papers, yeah? When you understood what I've done here, what it means here, you can write an abstract saying, we looked at this thing, this is how I did the thing, these are the major findings. So, abstract. Any questions? Now, I'm not going to read the stuff beforehand, like many students send you stuff saying, will you please read this and see this right? No, that's your assessment, right? I look at the thing when you've done the thing. Yeah? But if you have issues like not sure of some particular aspects, you want some clarification, I can certainly look at that for you. Yeah? And I hope you won't have any R errors. As far as R goes, to turn wide into long format, there are many avenues available. Essentially, you can use things like reshape data. We'll do that for you. I think also in probably something like, now which package is it? I think it's probably dplyr, maybe dplyr or reshape also has this melt function. Melt is in dplyr? Yeah, melt function does a similar thing. So you can actually, and you'll find lots of these kind of things. You can actually take wide format into long format and backwards as well. That's what this does here. So you can find those particular syntaxes online. They're all available to you with examples. Pick those out, change your context, your data, whatever variables. You'll find that it works very well. One thing you can do, though, of course, is that once you've done that, you can look at tables of the data to work out whether the number of observations under each of the levels is as that were in the original data, to make sure they're correct. And just check a few records to make sure they line up properly, right? To make sure that it's done properly. In case you've messed up somewhere and it's actually scrambled the whole thing, you don't want that to happen. Yeah? What do you think? What do you reckon? How many do you expect to find? I would expect you'll find about 5 or 10. I wouldn't expect much more than that. Find relevant references. You might sometimes refer to something saying this also looked at this kind of data here beforehand. The thing with references and your introduction will be you'll tell us who did the work. So citation of any kind you like, any kind of citation, any kind of referencing you like will work for you. So you'll need to refer to the author and year, maybe, saying so and so did this work. So you say author, for example, you're saying something like, Siblis 97 in brackets did this. That's okay. Or you can say things like this work was done, and you can put the bracket somewhere. For example, you can say other research found this, and you can find. Then you can say put the researcher's name and year in brackets as well. Or you can refer by number 1, 2, 3, 4, 5, 10. You can refer to the thing as citation one, number one, number two. Anything that works for you is fine. I don't really care on the citation style. But if you get 5 or 10 references that are relevant, you must say who did the work, what the context was, what they found. Was it European context, Australian context, US context? That's different. That'll be interesting to know which country it's from, right? That's really all. About 5 or 10 will be great. If you can find more, by all means do so. But you will describe essentially the work they did and what it means, what they found, major things. So once you've done your work and completed your analysis, you'll compare it to what was seen before in your introduction, saying what is different or what is the same. So the results find discussion will be along the lines of what you found here and how it compares with what else has been found. Conclusion very short, maybe saying essentially how, going back to the question of interest, was how the availability of Medicaid and insurance affects the number of visits and the type of visits. Very quickly, in maybe a short paragraph, you can say the major finding. That's really all there is. All good? Yep. I'll be here. Good.
In the brief, it gives page limits for separate sections.
Yes.
In the results section, does that page limit include the inclusion of any graphs that we want to put in? Or is that just
the graphs and figures and tables are not part of the page count. And they're approximate. That's my guideline. I wouldn't think you need more than that. I think I've given you ample space there for what you should write, yeah? If you go over there, then it needs to be with justification. In other words, what you've got there is really relevant and useful. So don't write prose. This is not prose. This is a scientific report, a journal article of that kind, right? Prose is something else, and that's lovely to read as well, but no, this isn't prose. Be accurate to the point and precise and short if you can. All good? Yes, Salman.
When you are deciding between causing plus on one and the negative binomial, how do we just mainly look at the residuals, or is there something else we should also be checking?
The residuals is mainly what you'll be looking at. You'll also be looking at the estimates and standard errors, those kinds of things. Residual error, those kinds of things will be useful to you. Yeah. So Poisson and quasi-Poisson, usually you'll find with over-dispersed data will be much better to start off with. But if it's badly skewed, you'll find that negative binomial looks better than both of those. All good? All right. Thank you. We'll see you next week.